Hey guys, this is Mrs. Harbin, and today we are looking at 6.3 about the zeros and inequalities regarding quadratic functions. Let's start with a quick look at our biblical integration. We know that God provided 4 different gospel accounts in His holy word: Matthew, Mark, Luke, and John, and they provide us different insights to this same story, the story of Jesus. Graphing equations can help us see this written information from a different perspective. Instead of just seeing an equation with a bunch of numbers, we can actually see what it represents in graphic form, and it allows us to maybe see something that we didn't see before. Let's start with a quick warm-up here. Sorry, I am having issues clicking some of these buttons here. All right, we're going to state the vertex of each function. Remember that when there is no b term, our x value for our vertex is 0. And the others, you should be able to pull right out of this vertex form. So pause the video, see if you can write the vertex, and then see how you did. And hopefully you got 0, 7, 4, 11, and -2, 0. And you'll see my little note here. Y, that's a -2, because the formula is x minus h. So this x plus 2 is really x minus -2. Our h is -2. All right, let's take a look at the domain and range. Sorry, there's writing on the screen. I was working on this earlier, and I guess it didn't all get erased. But we know by looking at this that this is a quadratic function, so we know it's a parabola. We know then that our domain is going to be all real numbers. All parabolas have that same domain. Our range is determined by our vertex, and our vertex here is -1, 3. This is a parabola with a positive a term, so our parabola is going to be opening up. That means our vertex is a minimum, and our range will be above the vertex. So we're going to say that our range is greater than or equal to 3. All right, let's do another quick review on how to put this in vertex form, and there is a typo on this slide, so you'll see that in just a second. First, we're going to bump the constant. We know that we can't complete the square if we don't have a leading coefficient of 1, so we factor out that 2, and we get 2 times x squared plus 3x plus 9 over 4. And then we've got to balance that out. Since we added a 9 over 4 times 2 on the inside, we've got to add the opposite of that on the outside to balance it. So that's where our -18 over 4 comes through. Our 1 here simplifies to 4 over 4. And we get f of x equals 2 times, and then when we complete our square and factor, we get square root of the first, x, sine of the second, plus square root of the third, 3/2. All of that squared. And when we combine 4/4, -4/4 minus 18/4, it's -22 over 4, which simplifies to -11 over 2. So we needed to simplify that or correct that mistake there in the slide. All right, so keep this in mind. The y-intercept of the quadratic function in the form f of x equals ax squared plus bx plus c is 0, c. So y-intercept of the quadratic function. Basically, our constant term is our y-intercept. Now, we can state that fact, but we can also prove it by making all of our x's 0, because we know that at the y-intercept, x is equal to 0. By making all of our x's equal to 0, then all we have left is our constant term. The x-intercepts can be found by making our f of x 0 or our y 0. Okay, so let f of x equals 0, and then we'll solve for x. We're going to solve for x using the methods that we've been practicing. Remember that you can factor, you can complete the square, you can take roots, or you can use the quadratic formula. That will give us our up to 2 x-intercepts. Remember that a quadratic equation can have 2 x-intercepts, 1 or sometimes 0 real intercepts, but up to 2. A 0, also called a root of a function, is the value of x for which f of x equals 0. So previously, when we were dealing with linear equations, we were calling these x-intercepts. The terminology that you're going to hear when we talk about quadratics are the zeros of the function, or the roots of the function. It is still x-intercepts, but it's not called that as much anymore. A function's real number zeros are the x-coordinates of its graph's x-intercepts. pretty much another way of what we just said. The zeros are the x-intercepts. All right, let's take a look at this example. We want to find the y-intercept and the zeros of this function. Well, the y-intercept is easy. We just set our x is equal to 0 and look at our constant term here, and our y-intercept is 2. To find our x-intercepts, we've got to do a little bit more work. So we're going to set that function equal to 0, and we get 0 equals 1/2 x squared plus 2x plus 2. We're going to factor out this 1/2. All of this can be factored out. So remember, factoring is just dividing. So I'm going to take each of these and divide them by 1/2 and factor out that 1/2. When I do that, I get 1/2 factored out, and what I'm left with is x squared plus 4x plus 4. Remember, if you're confused how 2 divided by 1/2 is 4, come up here and do a little side work here. 2 divided by 1/2 is the same thing as multiplying by the reciprocal, 2 times 2 over 1. And 2 times 2 is equal to 4. So that's how we got that 4x and that 4. All right, once we've got that 1/2 factored out, we can go ahead and factor this. This factors nice and neat to x plus 2 times x plus 2. We still have that 1/2 here. I'm going to keep writing it, even though it's not going to help us find the 0 or the root of the function. I don't want to forget that we didn't go anywhere. We didn't change the value. We just changed the form. We're then going to take each of our factors here and set them equal to 0. Now, when we set 1/2 equal to 0, we know that's not true. So it's not going to matter. It's not equal to 0. But x plus 2 and x plus 2, when we set those equal to 0 and we solve by subtracting 2 from both sides, what we get is that x is equal to -2, and we get it twice. When you get this same 0 twice, that's called x equals -2 multiplicity of 2. What that means is that your parabola is not going to go through -2. So read our quick graph here. That parabola instead is going to touch -2. Instead of going through the x-axis, it's just going to touch the x-axis. And it kind of is like the root or the bottom of the parabola in that case. So when you get the same x-intercept or the same root twice, that's a multiplicity. So this is -2 multiplicity 2. And it means it's not going to go through the x-axis. Excuse me. All right, let's find the y-intercept and the zeros of this function. It's already in vertex form for us. We are going to set that equal to 0. Now, we can't just take our 8 and say that that is the y-intercept. Remember, we can only use that constant term when it was in the form ax squared plus bx plus c. This one is not in that form. It's in vertex form. So don't just assume that 8 is the y-intercept because it's the constant hanging out at the bottom down here. It's not in the correct form. So we're going to find the y-intercept by turning our x's to zeros, or our x to 0. So we get -2 times 0 minus 1 squared plus 8. And when we simplify all that, we get -2 times 1 plus 8, which gives us 6. So our y-intercept is 0, 6. In order to find our x-intercept, we're going to make our s of x and set that equal to 0. So we get -2 times x minus 1 squared plus 8. Our ultimate goal is to get this x by itself, so we need to kind of work our way out and work our way from the outside, work our way in. First, we need to isolate this set of parentheses. We're going to do the order of operations in reverse order. So I'm going to look and see if there's anything that I can add or subtract. And I see this plus 8, and I know that I can subtract 8. Then I'm going to look and see if there's anything I can multiply or divide. I see this being multiplied by -2, so then I can divide by -2. After that, I need to get rid of my exponents here. And the way that I undo exponents is with roots. So I'm going to do roots. So hopefully you see how I'm working my way backwards to the order of operations. I took care of this first, this second. Now I have to undo my exponent, and then last, I'll deal with what's in the parentheses. All right, so what we get after we subtract 8 and then divide by -2 is x minus 1 squared equals 4. At this point, we take the square root of both sides, and we get x minus 1 equals plus or minus 2. This is what students tend to forget. Remember, when you're taking the square root, plus or minus, we've got to come up with two possible roots here. If you only write 2, you're not going to get two possible roots, so make sure you write that plus or minus. We'll then set each of these themselves equal to plus 2, or positive 2, and 1 equal to negative 2. And from that point, solve for x. So I get x equals 3, and x equals negative 1. When I do the work there, so I've got my two roots. Notice this time, they're two separate roots. Unlike the previous problem, which just touched negative 2, these will actually go through the x-intercepts of 0, 3, and 0, negative 1. All right, let's find the zeros now of this function. P of x equals negative x plus 2 squared plus 6. We're going to set it equal to 0. And again, working backwards with the order of operations, first looking at addition and subtraction, we're going to subtract 6. Then we need to get rid of this negative sign. That's really a negative 1. So next we'll divide by negative 1. Then we're going to undo our exponents with taking roots. And when I take the root of both sides, I get x plus 2 equals plus or minus 6. Separating that into two equations, I get x equals negative 2 plus the square root of 6, and x equals negative 2 minus the square root of 6. If you needed to graph this, you would need to plug that into your calculator to get a decimal approximation so that you could graph it. And our decimal approximation for that is approximately 0.45 and approximately negative 4.45. All right, let's find the zeros of this. We're going to set it equal to 0. X squared minus 2x plus 3. And at first it looks like this might be one that's really easy to factor. But when I think of the factors of positive 3, I get positive 3 and positive 1, negative 3 and negative 1. And unfortunately, when I add 3 and 1, that's 4. And when I add negative 3 and negative 1, that's negative 4. It doesn't add up to my b term. So I'm not going to be able to factor. I'm not going to solve this by taking roots or by completing the square, so I do need to use the quadratic formula. We're going to identify our a, b, and c. So a is 1, b is negative 2, and c is 3. And plug away. We get negative b plus or minus b squared minus 4ac all over 2a. Please remember to use parentheses when you substitute. It's so important when we are dealing with exponents and when we're plugging into a formula that has negatives so that we make sure that our signs are correct. After we simplify that, we get 2 plus or minus the square root of 8 over negative 2. Just by looking at this, we know the square root of 8 is going to give us an imaginary number. And that tells us that we don't have any real roots. When we simplify that, we get 1 plus or minus I root 2. So our final answer would be no real roots. So a quadratic function, like I said earlier, and like we've talked about earlier, has either two real roots, a double real root, that's the multiplicity, or two complex roots. Those are your different options. The solution to a single variable quadratic equation or an inequality can be found graphically by finding the zeros of its related quadratic function. So if you're trying to find an inequality, a quadratic inequality, you can solve the quadratic equation, the related quadratic function, to find those same roots. It applies whether you're using dealing with an inequality, or dealing with an equation. Graphing quadratic inequalities is similar to graphing linear inequalities, and I'm almost out of time here. First, we want to graph the related function. We're going to use a solid or dashed curve, solid if it's greater than, equal to, less than, or equal to, dashed if it's just greater than or less than. And then we're going to shade the appropriate region. And I always tell students, start with the vertex. If it's greater than, equal to, or greater than, start wherever the vertex is and shade up. Okay, if the vertex is here, then you're going to shade here. If the vertex is here, you're going to shade here. So start with the vertex and shade up. And then conversely, if you're dealing with less than or equal to, start with the vertex and shade down. All right, I'm not going to be able to explain this last one, so let's take a look at it really quickly. The steps for graphing a quadratic inequality.